Hi, I'm Tobin Porterfield. Welcome to Module 4A, where we're going to take a look at random variables. First off, a little orientation of where we are. We've made it through Module 1, 2, and 3, where we've explored probability, messing around with data, and now Module 4 is going to take something of an extension on what we've done on probability and show some other applications of that. After that, we'll wrap up with Modules 4 and 5, any other loose ends, and our final exam. So let's get started. First, some foundational terms. Now, we've talked about randomness already, but keep in mind a random variable is the result of some random event, and we define randomness as any outcome is equally likely. Now, along those same lines, a little distinction is a discrete random variable, and that would be the case where we can specifically list all possible outcomes. So rolling a die would be a discrete random event that would provide discrete random outcomes or variables of a 1, a 2, a 3, a 4, a 5, or a 6. In another situation, though, would be a continuous random variable, and that's where the outcome variable could take on any value within a range that we're working within. So let's say age actually could go either way. For age, if we required that we would only measure age based on the year or only on the decade, those would both be discrete random variables. So your age would be 31 or 32 or 33. But if we allowed that variable to be continuous and said, no, we want to know your exact age, then your age might be 40.126, 40.234, or so forth. So remember, a continuous random variable, we're just going to have a whole series of potential outcomes. The discrete random variable, there'll be very specific events that we can identify. So let's put that to work. We're going to focus first on the discrete random variables. When that probability model is known, then the expected value can be calculated. If we go back to our dice model, we know that there are 6 outcomes. We can roll 1, a 2, a 3, a 4, a 5, or a 6. We know the likelihood of each of those outcomes would be 1 divided by 6, or 0.17. So we could multiply each outcome times its probability and sum those up. And so 1 times 0.17, 2 times 0.17, 3 times, and so forth. And if we sum those up, our expected value would be 3.57. So while I don't ever expect to roll a 3.57, over time and continuous experiments, I would expect on average that my total would be approximately 3.57. So just a simple application of it. We'll take it to something a little more practical in just a minute. And here it is. An insurance company sells policies covering death and disability. The policy pays $100,000 for death and $50,000 for disability. So we have our outcomes. You're either going to be awarded nothing because you don't die this year, or if you die this year, your family will be awarded $100,000, or if you are disabled this year, you'll be awarded $50,000. So there really are only 3 outcomes. They are discrete outcomes. The probabilities are provided here. Death is 1 in 1,000. Disability is 2 in 1,000. Now keep in mind as well that nothing may occur, which would then be 997 in 1,000. And so if we're going to calculate our expected value, it'd be helpful to put this all out on a nice table. We have our payouts. We have our probabilities associated with those. And I expect you're looking at the screen already and saying, well, hold it. If the payout's 0, do I really need to worry about this? Because when I multiply 0 times that probability, I'm still going to get 0, and that's great. You're absolutely correct. However, we do not want to lose sight of that event, that nothing might occur, because it will affect when we calculate the variation and the standard deviation. So it's just better to keep it in play right now, because there are actually 3 outcomes, and we've got them all captured here. So the expected annual payout, or what we would call the expected outcome, E of X, we would multiply each of the outcomes times those probabilities. We have all that information, and then we would sum those up. And on average then, the insurance company would expect to pay out $200 per policy. Now we know that the actual results are going to vary significantly from there, because they're either going to pay out 0, 50,000, or 100,000. But on average, as an expected annual payout, it's $200 per policy. Now let's push it a little bit further and take a look at what the variation is and the standard deviation. Now this works the same as when we worked with standard deviation and variation previously, looking at data, where we'll take the observation, in this case $100,000, the outcome, minus the average, which was $200. We'll square that result, and then we'll multiply it times its probability, and we'll do that for each of the three outcomes. There we have them set up again, our three outcomes and our three probabilities, and we multiply those out. Now notice here, this is where that 0 starts to become important because we are going to take that into consideration now. So we sum those up, and that will actually give us our variation, which is rather large due to the squaring effect, 14,960,000. Now keep in mind there's no unit of measure on this, because with variation the squaring removes the validity of the unit of measure. But when we take the square root of this in order to create the standard deviation, dollars come back into play. So our standard deviation is actually $3,867. Now I hope that's already starting to register with you that that is a rather large standard deviation compared to a mean that's relatively small. And that is one of the challenges certainly that insurance companies would face, is that there is great variability in what their payout would be. And to put a little measurement on that, I'd like to introduce the coefficient of variance. Coefficient of variance is just a ratio of the standard deviation relative to the mean. C of V is how we write it, and the simple equation is the standard deviation divided by the mean. And in our example of our insurance policy, we see that that value comes back as 19. Now I wanted to introduce this, and I do want you to tuck this away, but right now that value 19 doesn't have much meaning to us. But I warn you, that's a comparative value. So if we adjust how our payouts work, or we adjust the probabilities, then we would see some change in this, and hopefully we would see a much smaller number, which would reflect that our amount of variance relative to the mean has gone down. So this is a relative measure, and it doesn't have much meaning unless we can compare it to something else. All right, let's try a different example. Bookstore purchases. This coincides with problem 3, I believe, at the back of this chapter in your book. But let's just go through this one once. We've got a little different situation. Suppose the probabilities of a customer buying a book in my store. They might buy 0 books, 1 book, or 2 books. Those are discrete outcomes, right? They can't buy 1.3 books, 2.1 books. They'll buy 0, 1, or 2. The probabilities associated with that are 20%, 40%, and 40%. So I expect you're already thinking, I can set that easily up in a table. I can multiply those across, add those down. I'll have my expected purchases by customer, and then I can also calculate my variance and subsequently my standard deviation in order to understand how much variability exists in this model. So let's give it a shot. Here's my table. I can multiply 0 times 0.20, 1 times 0.40, and 2 times 0.40 and come up with my expected outcome, which will be 1.2. So on average, I can expect that a consumer will buy 1.2 books while visiting my bookstore. Now to take that again a step further, we'll calculate the variance by subtracting the outcome from the mean, so 0 minus 1.2, 1 minus 1.2, and 2 minus 1.2. We'll square those results and then multiply each one times their respective probability, sum those up, and I get 0.56. Now that's starting to look like a relatively small amount of variation compared to the mean, which is absolutely true. So as a bookstore owner, I have a little bit less, I forgot to calculate my standard deviation, take the square root of that, so it's 0.74, which is still a relatively small variation relative to my mean. Take a look at how to model some changes or alter some of our data. One method is to add a constant. Adding a constant means, let's look at our insurance example, where we're paying out $50,000, maybe we're going to pay out an additional $5,000. So that constant would be $5,000, and our payout would change from $50,000 to $55,000. Similarly, that same constant then would be added to our death payout, which was $100,000, and it turns it into $105,000. So look at these equations that are presented here. There's our $100,000 plus the $10,000. That's simple enough. look what happens at our variance and our standard deviation. That same effect comes in. So adding simply increases, or subtracting simply changes the values that we've already calculated. This is important because another alternative would be to actually multiply and add in a value. So if we decided we're going to double our payouts on that insurance policy, and so instead of paying out $100,000, we'll pay out $200,000. Instead of paying out $50,000, we'll pay out $100,000. Then look at what happens here. Not too surprisingly, our expected value, the constant is listed here as an A, so it would be 100,000 times 2, 200,000. That's not too hard. But look what happens with our variation. We actually increase our variation by a factor of 4 because we take the 2, the doubling, and we square it. And then that'll translate out when we calculate our standard deviation. So one effect that I hope you're noticing already is that if we add, it's rather simplistic that we'll just increase appropriately or decrease appropriately our expected values and our variance and standard deviation. But if we multiply, it's going to have an extremely large effect on our variation and then our standard deviation. All right, another little reminder, don't forget about our addition rule from the last chapter. And our addition rule told us that if we had two probabilities for two independent events and we are equally happy with either event occurring, then we would add those together. Similarly, the addition rule for variances are if those two outcomes are independent, then we can simply add those two together. We'll have a little more use for that shortly, so I just wanted to get that into play for us. All right, one last one. Now let's try it out. The expected annual payout per insurance policy is $200,000 and the variances is $14,960. We had that. The standard deviation, $3,868, calculated earlier. Now what happens if we double that payout? We take 2 times the expected value. So instead of the expected value being 200, it becomes 400. The variance, though, instead of just simply being doubled, we see that 2 squared, so it's going to be a factor of 4, will be 59,840,000. Quite a large increase comparatively to where we were. But the means stay relatively consistent. Let's take a look at a little different cut at this insurance example, and that is, what if we look at the payout of 2 customers under the old model? So the average is $200 for you and $200 for me. So it's 2 times that. It's $400, or it's the 2 added together, $400. And our variance, $14,960, is simply added twice because you and I are independent policy owners. And if they were curious about the result of having 2 policies or 3 policies or 4 policies or 100 policies, then we simply add those together to see the effect. All right, let's give these things a try. I've selected some sample problems from you. If you're using the hard copy textbook, then I recommend problems 1, 2, 4, 5, 6, and 7. Problem 9 gets into the doubling effect of using a constant. So that one's a little separate. 1, 2, 4, 5, and 6 deal with the problem similar to what we were looking at with the insurance problem and the bookstore problem. If you're using my stat lab, then I'll have set up a unique assignment online for you. So give it a try, and then let's move on to part B.
On that